All right, here's my fun little presentation about implicit differentiation. You know, that rhymes. Wonderful. All right. Uh, cool. Slide one. Nice, nice. Differentiation, as you can see. Here we'll be deriving this function, this beautiful little function over here. It's pretty cute, honestly. 2x squared times y to the 1/3 power minus 2 equals 0. Honestly, it's pretty nice, pretty nice. Here we're going to be literally just moving everything around, you know, putting y on one side and, you know, everything else on the other side, just doing some division, all that, and then deriving so that y is the derivative of what the other side would be. Wonderful, wonderful. Literally just how math works, honestly. Pretty good, pretty good. All right, boom, bada bing, bada boom. Literally right here, as you can see, the math to do exactly what I said that we'd be doing. Kind of great, if you ask me personally. Yeah, as you can see, I just moved everything around from steps 1 through 4, and then actually no 1 through 5, honestly, and then step 6, literally just some basic calculus on it. Like no, like honestly, you got this already. It's pretty breezy, okay. Now get this. There's a different kind. There's a different kind of differentiation, right? Implicit differentiation. Wonderful, amazing. You see, the other thing was so great, so easy, so simple, but we can greatly make it incredibly difficult, like absurdly more confusing by introducing other factors. For example, by using wacky derivatives. Yeah, read the slide. I'm just going off the cuff here. I don't have much time. Anyway, here, implicit differentiation, as you can see, it's just like differentiating normally, but like every time you derive something, like every time you use the power rule, the quotient rule, product rule, blah blah blah, you're going to take whatever bit you took from the whatever bit you derived just now, and then you're gonna add that little fraction over there, right there, okay? And at the top, you're gonna put the variable that you were deriving, and at the bottom, you're gonna put the variable that you're expecting. I was never told exactly what that means, but you get the concept after you see it a bit, So yeah, read the slides a bit and go ahead. Nice, cool. Here's example A. Of course, I already worked it out for you. You can already see that in the absolutes of absolutes. As you can see, I did not do the example from before. It's just another funny little example. As you can see, just like regular differentiation, you just differentiate and then tack on that little bit at the end, right? As you can see, there's none for the x factor because, well, that would be dx over dx. Doesn't make any sense. That's just a 1. But for the y factor right there, at the top, variable that you're differentiating, bottom, variable that you're expecting, differentiating blah, blah, blah with respect to x. I didn't write that down here, but, just assume it, okay? Because it's on the bottom. Okay. Yeah, looks pretty good to me, honestly. That's literally just how you do it. It just makes sense, honestly. Pretty good. Okay. Example B, pretty neat. As you can see here, it's literally just the exact same things before, except it's not actually done. You see, quotient rule takes up a lot of space. Anyway, here's another equation. We're differentiating it with respect to x. X over y cubed equals 1, blah blah blah. Quotient grid, as you can see, x turns to 1, y cubed turns into 3y squared, dy over dx, because tack on the thing. Nice. Okay, here's the continuation of it. Yeah, pretty nice. Honestly, as you can see, I made a little fraction thing, as I should, and then I basically just solved it in reverse so I could get the little dy dx alone, taking it out the top of the fraction, blah blah blah, and then putting it on its other side, and then bada bing bada boom, you get y over 3x for dy over dx. Pretty beautiful if you ask me. Yeah, pretty neat. Anyway, here is my favorite one, personally, my personal favorite, like top 10 for sure. 4x to the 4th plus 3y squared minus 8z cubed plus 2f to the 6th power equals 0. Now, looks confusing, right? Looks pretty wacky. But get this. We're deriving with respect to t, not x. So, you can ignore the fact that x is there, just treat it as another variable, like off the street or something, okay? And you'll find that you can just keep deriving, honestly. Just look here. It's wonderful. It's beautiful. It's just the same thing that you've been doing, but you just put on d whatever over dt because you're expecting t, and you're just deriving the variables. So yeah, that's about it. Good job.